Hi everyone, welcome back to the channel. In this video, we are discussing about common gate amplifier using N-channel enhancement type MOSFET. We will analyze the circuit behaviors performing DC analysis and also AC analysis and determine the key parameter through step-by-step calculation and spice simulation. And our aim is to calculate the voltage gain, that is AV is equal to V out divided by V in. Let us start by examining the circuit. As you can see here, we have a biasing resistor R1 and the resistor R2 and RD and the RS. And we also a load RL and input voltage Vi and the DC voltage source VDD as 20 volt. Notice the capacitor C1 couples the input voltage source at the source node. C2 AC couples the load at drain node. This is the source node and this is the drain node and this is the gate node. And C3 grounds the gate terminal. Hence the name called common gate amplifier. The N-channel enhancement MOSFET has specific parameter including the threshold voltage VTH is equal to 3 volt and conduction parameter the Kn is equal to 6 milliamps per voltage square. We will see how to input this into the SPICE module later. Let us begin with the DC analysis. For this, the capacitors are treated as a open circuit C1 and C2 and C3. This simplifies our circuit, removing the load and the input source. And our simplified circuit looks to be like this. Okay, and here drain current is flowing from this direction. Similarly, the source current is flowing in this direction and the gate current is 0. Now we are left with the 4 resistor and VDD and the MOSFET. And we will call this as a node G for the reference. Before proceeding, we will assume that the MOSFET is in saturation region. And to prove this, we require two conditions. That is VGS, the voltage between gate to source, is greater than or equal to threshold voltage, the condition number 1. And similarly, the VDS, the voltage between drain and source, this VDS is greater than or equal to VGS minus VTH. Verify the condition later. First, let us find the gate voltage VG. Okay. Since the gate current is 0, we can use the voltage divider rules with the R1 and R2 to find voltage VG. We can write VG is equal to R2 divided by R1 plus R2 into VDD, which is equal to, here we are considering it as a 2 mega ohm and this R2 as a 2 mega ohm and VDSD as a 20 volt. 2 into 10 to the power of 6 divided by 2 into 10 to the power of 6 plus 2 into 10 to the power of 6 into 20, which is equal to 10 volt. So our gate voltage Vg is equal to 10 volt. By applying this Kirchhoff voltage law at the input terminal, we can relate the Vg and Vgs and the voltage across the resistor Rs, which is depends upon the drain current Id, since the gate current is 0. So we can denote it as Vg is equal to Vgs plus Rs into Is. Here Vg is the gate voltage and Vgs is the gate to source voltage, and the Rs is the source resistance, and similarly Is is the source current. And here, due to the gate current is 0, the drain current Id is equal to source current Is. And in saturation region, the drain current Id can be given by Id is equal to Kn into Vgs minus V threshold volt to the whole square. And it is valid when the MOSFET is in saturation region. Substituting this ID into our this equation, we can write it as Vg is equal to Vgs plus Rs into Kn into Vgs minus Vth the whole square, which is equal to 10 volt equal to Vgs plus, here we are calling Rs as 1 kilo ohm. So the 10 into 3 into, and our Kn, the transconductance, as considered 6 milliamps per volt square. Okay, we have already defined it that. So which is equal to 0.006 into Vgs minus 3 whole square. It's the threshold voltage. So that the 10 volt is equal to Vgs plus 6 into Vgs minus 3 to the whole square. If we solve this quadratic equation by using quadratic equation calculator, we will get two value, which is Vgs is equal to 1.833 volt or Vgs is equal to 4 volt. However, only one value satisfies our saturation region, that is Vgs is greater than or equal to Vth. That means our gate to source voltage Vgs we can consider as 4 volt. So we choose the valid Vgs and calculate the drain current. And in saturation region, the drain current Id can be given by Kn into Vgs minus Vth whole square. By plugging this value into our equation, we can return as 0.006 into 4 minus 3 to the whole square. So that the drain current Id is equal to 6 milliamps. Now we must verify second saturation region condition. We can determine VDS by using the Kirchhoff voltage law at the output loop. As per KVL, the VDD is equal to RD into ID plus the voltage, drain to source voltage, VDS plus IS into RS. And we know that due to the gate current 0, IS is equal to ID. And we can group them together. We can rewrite it as VDS is equal to VDD minus ID into RD plus RS. Okay, which is equal to 20 minus 6 into 10 to the power of 3 into 2000. It is RD. Here 2K it is 1K. Okay, plus 1000 ohm, which is equal to 2 volt, and which is greater than VGS minus VTH, which is 4 minus 3 volt is equal to 1 volt. By substituting this value, we had confirmed that VDS is greater than VGS minus threshold volt, and confirming our MOSFET operate in saturation region, and our assumption was correct. The MOSFET operated in saturation region. Let us move on to DC analysis. So we have our DC quantities. Let us compare this with our simulation result. Okay, here our simulated result. As per the calculation, our drain current is 6 milliamps. Okay, and the drain to source voltage is equal to 2 volt, and gate to source voltage, which is equal to 4 volt. As you can see here, the simulated ID and VGS and VDS values closely match to our calculation. It is important to understand how the MOSFET is modeled in the SPICE. We have used N-channel MOSFET, and we need to input the parameter like the threshold voltage. You can see here the threshold voltage is 3 volt, and the conduction parameter Kp as 12 millisiemens. The Kp is related to the conduction parameter Kn. Then Kn is equal to Kp divided by 2 into W divided by L. So which is equal to Kp into 2. By considering our MOSFET, the W will be 10 to the power of minus 5, and similarly L will be 10 to the power of minus 5, and so that the Kn is equal to Kp divided by 2 into 1, and here the Kp is defined as the gain beta of the MOSFET, so simply Kp is equal to 2 times Kn. This is the crucial for setting up the SPICE model correctly, so that we have considered here Kp as a 12 millisiemens, because our Kn is 6, so into 2 it is a 12 millisiemens. Now let's move on to AC analysis. We use small signal model for this. Notice that the capacitors are considered as a short circuit in the AC analysis. This simplifies the circuit. For example, C3, the capacitor C3 shorts the gate to the ground. This is our simplified circuit. For example, this C3 shorts the gate terminal to the ground, and VDD also we are considering as a AC ground, which simplifies how the resistor are treated. If C3 got shorted, gate terminal and directly connected to the ground, and similarly here R1 and the R2 connected to the ground and the AC ground. That's why we are not seeing the resistor R1 and R2 in the small signal model. The going to the drain node here, the resistor RD going to connect the AC ground and the resistor RL going to connect the ground, and the capacitor C2 act as a short circuit in the AC analysis so that the drain resistor RD is parallel to the RL. Similarly, the one pin of the resistor RS is connected to the ground pin and C1 got started. Again, the resistor RS is parallel to the Rin. By defining the current by applying the KCL, we can establish the equation relating to ID, the input current as In, and the current to the resistor as IRS. We can express this current in terms of VGS, Vi, and the resistor value. Before we started, the In flowing from this positive in this direction and the IRS in this direction, so that the drain current ID plus the input current In equal to IRS. The ID can be determined by the circuit, that is ID is equal to Gm into VGS, and the current In is equal to, and the current In is equal to V in Vi input voltage and the voltage at this node minus of minus VGS, because the negative terminal in this source node, and it is divided by resistor Rin. So which is equal to Vi plus VGS divided by Rin, and the current across the resistor Rs, which is IRS is equal to, minus VGS by Rs due to this reverse polarity. Let us substitute the value into this. That is ID plus In is equal to IRS. Okay. So that ID is equal to Gm into VGS plus Vi plus VGS divided by Rin is equal to minus VGS divided by Rs. So that Gm into Rin into Rs VGS plus Vi plus VGS into Rs is equal to minus VGS into Rin. So when we simplify this, we will get 1 plus Gm into Rs into Rin plus Rs into VGS is equal to minus of Vi into Rs. Vi can be noted as minus of 1 plus Gm into Rs into Rin plus Rs into VGS divided by Rs, which we can notify as equation 1. We need V out, that we need the resistor and the current flowing through the from drain to the ground. But the current flowing through drain to source and it is going in reverse direction. So that we can denoted V out is equal to minus Gm into VGS into RD parallel to the RL. We can notify as equation 2. And we know that voltage gain AV is equal to V out divided by Vi. When we substitute equation 1 and equation 2 to this gain, that the AV is equal to Gm into Rs into Rd parallel to Rl divided by 1 plus Gm into Rs into Rin plus Rs. And by considering Rd and Rl is parallel, which means that the Rd and RL is parallel, which is equal to Rd into RL divided by Rd plus RL, which is equal to, as per the value, it is Rd is equal to 2 kilo and the RL is equal to 6 kilo. So that 2 into 10 to the power of 3 into 6 into 10 to the power of 3 divided by 2 into 10 to the power of 3 plus 6 into 10 to the power of 3, which is equal to 1500 ohm. This is 1.5 kilo ohm. Here the Gm is the AC parameter and it is determined by ID, which is equal to 6 milliamps, and conduction parameter Kn is equal to 6 milliamps per voltage square, and which can be substituted the equation Gm is equal to 2 times square root of ID into Kn, which is equal to 2 times square root of 0.006 into 0.006, which is equal to 0.012 Siemens. Once we substitute this value into our gain, we will get AV is equal to 0.012 into 10 to the power of 3 into 1500 divided by 1 plus 0.012 into 10 to the power of 3 into 500 plus 10 to the power of 3, which we simplify that, we'll get AV, the voltage gain is equal to 2.40. Let us verify this with our simulator. The transient response shows our input and the output waveform. By measuring the peak to peak voltage, we can calculate the gain and compare it with our calculated value. So as per simulation, our input voltage, the peak to peak value is 20 millivolt, and similarly our output, the peak to peak value around is almost nearby 24 millivolt, and the input and outputs are in the same phase. By measuring the peak to peak value of output, it is approximately equal to and 23.9 and minus 24.7, which is approximately equal to 48 millivolt. So that voltage gain AV is equal to peak to peak value of output voltage and the peak to peak value of input voltage, which is equal to AV is equal to 48 millivolt divided by 20 millivolt, which is equal to 2.4 as a voltage gain. The simulation result closely matches our calculation, confirming the accuracy of our analysis. Finally, let us examine the effect of the source resistance Rin on the voltage gain. In the ideal case, when the input resistor Rin is equal to 0, the voltage gain AV is equal to Gm into Rd parallel to the RL, because this section of this formula will get 0. So the RS will cancel out. So we'll get the final result is 0. And if we calculate this, we'll get around 18 is the maximum gain. This is the maximum voltage gain. Similarly, if we consider the Rin as a infinity, we'll get the voltage gain will be 0. This is the minimum voltage gain of the amplifier. This demonstrates that the common gate amplifier like the common base amplifier is best suited for the application with low output impedance source such as the current input applications. Considering this chart, if we decreases means if we minimize the resistor Rin, that our gain will be maximum, and similarly if we increases the resistor Rin value, the gain will going to reduces. This concludes our example for common gate amplifier using N-channel enhancement MOSFET. If you have any question or comments, please leave them below. Don't forget to like and subscribe, and share this video to help others learn about these topics. Thank you for watching, and see you in the next video.